Now we're going to solve a problem using radical reactions monochlorination. We're going to give the number of products, and we're also going to calculate the yield, approx yield, using relative reactivity. So this table is showing you that if you take the primary hydrogens as your reference, this is rate 1. And so what this is saying is that when you have chlorination, the secondary product will form 4.5 times faster than the primary. And you have a 5.1 for the tertiary position. Now, bromine is much more selective, and you will have 82 respect to the primary position. The secondary reactivity, relative reactivity is 82, and 1600 for the tertiary. That's saying that pretty much when you do bromination, you get almost one product. If that is the more stable radical is a preferred product, and when you have chlorination, these are relatively close, and that we can get several products. That's essentially that. So we're going to be first determining the number of products, and then using that information to calculate yields. So this is your product. Let me say, what is this? Let's do the monochlorination products of 2-methyl butane. And now your first step always is drawing the compound. So we have butane, 4 carbons, and 2 methyl. So 1, 2, 3, and 4. Now once we have that, let's determine the number of products. And so we're going to be looking at positions that are different in positions that are equivalent. So notice that here, I could have actually numbered the chain 1, 2, 3, 4, which means this position is equivalent to that. So that will lead to one product. So I'm going to draw that one first. The first product, say that I replaced one of the H's there. That's product A, let's call it that. Now, if the substitution occurs, there is a hydrogen at carbon 2, which we can replace by the halide. So the other product is, say, doing the at angle. Doing the substitution here. Say that that's my product B. And that is actually a tertiary position, as you can see. Another product that can form is if I replace one of the H's in 3. So I'm going to have this product. In this product, that's, let's say, this was tertiary here. That is actually secondary. That's primary. And now we're going to be using this to calculate the percent yield of each one of them, to estimate that. The final product, here I have another position, but what I want you to see is that if I replace a hydrogen there, I am going to get a product that is actually different. This is a primary again, but this is a primary product that's different from that. So we need to take that into account when we do the calculation. So we cannot group this hydrogens, 6 hydrogens here with this, because these lead to a different product. So total products, we have, looking at a stereochemistry, we'll have 4 possible products. Analyzing a stereochemistry, that's not a chiral center, so it's only 1. Here you have a chiral center, so this will be racemic product. This is not a chiral center, that's not. So we will have 5 products overall taken into account as stereochemistry. Now let's calculate what is the yield that we will have. And again, now we have, I have named this product B. So to keep that, let's call that C, and let's call that B. And now we're going to make another table. So how much of each of the products I can form. So now I'm going to have product type A, and B, C, and the products are there, right? And D. Now here we are going to count, we know this is primary, but we're going to count the number of H's that are equivalent. So, and that will raise to product 8. So now you have 3, and 3 is 6 hydrogens. And the relative reactivity of the primary hydrogens with chlorination is 1. Right. So now I have product type B is tertiary, so B is tertiary, and how many do I have? I have only 1. What is the reactivity of the tertiary? 5.1. Now I have product type C. How many H's do I have equivalent there? I have 2. Reactivity for those is 4.5. Finally, product type D. These are 3 H's that I can replace. I'm going to put a 3 here. Relative reactivity is 1. So now what we're going to do is multiply the number of H's by the relative reactivity. And this will give you 6. This will give you 5.1. This will give you 9. And this will give you 3. Now, the total reactivity, I'm going to add those up here. And now what we have here is that you're multiplying the number of hydrogens at a given position, giving the product, for example. So these are 6 times 1, the relative reactivity of a primary hydrogen, so that's 6. And here you had product type B is tertiary. You have only 1 H here. So it's 1 times 5.1 is 5.1. Position 3, so leading to product C here, you have 2 H's, so 2 hydrogens that are secondary. Secondary reactivity is 4.5. That multiplied is 9, and here the fourth product D, is a primary position. You have 3 hydrogens there, and so here you have 3. Now adding those numbers up is 23.1. To have the percent of each of the products, you will divide this number by the total reactivity. So the reactivity at that position over the total. So 6 over 23.1, that's 25.9%. And 5.1 over 23.1 is 22%. 9 over 23.1 is 38.9%. 3 over 23.1 is 12%. That is you're 100% up. But what it says, if notice that if this was a statistical distribution, you will have much more product of primary hydrogens because you have many more. You have here total 9 hydrogens there, but you have to take into account reactivity. Notice that the tertiary is only 1 hydrogen of all the hydrogens that we have in the molecule. Yet you get a significant amount of that product. So this is how you will estimate then the yield of the given positions. Remember to check where the positions are equivalent or not. Here we have determined that product type A is different than product B, even though they are primary, same reactivity.